Students, welcome to our YouTube channel Experience Tutor. Today we'll discuss class 11th physics. Get more than 95% marks series. Today's chapter is System of Particles and Rotational Motion. Chapter 7 NCERT Line by Line Part 2. So in the last class we have done the whole introduction part, that is 7.1 section, that is section 7.1. Now in today's class we'll do section 7. We'll start with section 7.2, center of mass. So what is center of mass? Center of mass is a concept which can be explained with the example. Say this is a rigid body and this is moving. At any point in time, if this rigid body can be represented as a point, can be replaced as a point, and this point, the whole mass of the body is concentrated on to that point. This point is known as the center of mass. So this is the concept. Now in this paragraph, in the first paragraph, we are trying to find out the center of mass of a two particle which are distance apart and which has some mass. So let us see how we find it out. So in simple language, whatever it is written in this paragraph, I am describing from the figure that let two particles are there, particle 1 and particle 2. Particle 1 has a mass m1, particle 2 has a mass m2. Particle 1 is separated by a distance x1 from the origin. Particle 2 is separated by a distance x2. X2 will be here from the origin. Now we have to find out the center of mass of this two particle system. So let us consider that X is the center of mass and it is separated, it is passing from through a point C in the x-axis. All the 3 points are in x-axis and we are measuring the distance of all the 3 points from the origin. So the center of mass X is equal to m1 x1 plus m2 x2 upon m1 plus m2. So this is the center of mass in this case. So in simple language we have described this whole paragraph. Now some special cases. Say till now we got x is equal to m1 x1 plus m2 x2 upon m1 plus m2. Let us consider that m1 and m2 are equal and they are equal to m. Then replacing m1 and m2 in this equation, we'll get x is equal to m x1 plus m x2 upon m plus m. We can take m common, so x1 plus x2 upon 2m. So mm get cancelled, So x is equal to, now the center of mass in this case is equal to the middle point, bit or midway. So here in NCERT they have come up with this result, and so if the masses are equal, then the center of mass will be the exactly the midway between them. Now if there are n particles, then and all are lying in the x-axis, then the center of mass will be, so then center of mass will be, can be written as, say, x is equal to m1 x1 plus m2 x2 plus dot 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 m mi or mn xn upon m1 plus m2 plus dot 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 mn. In this way we can write it the same way they have written here. This can again be written as sigma. This whole numerator can be written in sigma, in the form of sigma, that sigma mi xi upon the denominator can be written as sigma mi. Now sigma mi means the mass of each of the particle, summation of the mass of each of the particle present in the system. So that means the total mass of the system, which can be written as m, capital M. So this, in this term, in this sentence, the author meant to say the same, that the total mass of the system, that means sigma mi is equal to capital M. Now if, now here till here it is done. Now for n particles, what will be the mm, what will be the statement we have done it. Now we'll see the statement for the three particle system. It is very simple, like two particle system. So the center of mass, say 3 points are x1 y1 x2 y2 and x3 y3 respectively, and their masses are m1 m2 m3, and the center of mass c of the three particle system can be defined as a coordinate x and y, and then x can be written as m1 x1 plus m2 x2 plus m3 x3 upon m1 plus m2 plus m3, and y is can be written as m1 y1 plus m2 y2 plus m3 y3 upon m1 plus m2 plus m3. For the particles equal, again if we are taking the into consideration that if the masses are equal, if m1 is equal to m2 is equal to m3, which is equal to m, then we can write x is equal to m common x1 plus x2 plus x3 upon 3m. Get cancelled, and x1 plus x2 plus x3 upon 3 is left. Simple mathematical calculation, nothing else. Similarly, y can also be written as y1 plus y2 plus y3 upon 3 upon 3. So for we have found the center of mass for a three particle system, and we have considered a special case where all the masses are same. m1 is equal to m2, m is equal to m3 is equal to m. So in that condition we have found the x and y coordinates of center of mass. This can also be written as sigma mi, x coordinate can be written as sigma mi xi upon m. and y can also be written as sigma yi upon capital M, and z can be written as sigma mi zi upon capital M. Now, all the three coordinates in x, y, and z axis are written in this equations. Now, if we want to see the vector representation of it, then we have to consider that Ri be the position vector of ith particle and R be the position vector of the center of mass. In that case, we can write R1, here there is some printing mistake. So R1 is equal to xi unit vector I plus yi unit vector j plus zi unit vector k. Similarly, position vector R can be written as capital X I unit vector, capital Y j unit vector, and capital Z k unit vector. Now we can write the same thing, position vector R, as sigma of this thing. So we can write as sigma mi ri upon capital M. So R can be written in this form. Now few important concepts are here. Let us go through the concept. Note the economy of expression we achieve by the use of vector. If the origin of the frame of reference, the coordinate system, is chosen by the center of mass, then sigma miri is equal to 0 for a given system of particles. A rigid body such as matter, metastics, or a free will is a system of closely packed particles. Equation 7.4a, 7.4b, 7.4c, and 7.4d are therefore applicable to rigid body. The number of particles, atoms or molecule in such a body is so large that it is impossible to carry out the summation over the individual particles. In this equation, since the spacing of the particle is small, we can treat the body continuous distribution of mass. We subdivide the body into n small elements of mass, that is delta m1, delta m2, delta mn. The ith element delta mi is taken to be located about the point x, xi, x1, I1, y1, z1, the coordinate of the center of mass, then approximately given by. So in that case, if we take small elements, then in that case, x is equal to sigma delta mi xi upon sigma delta mi. Y is equal to sigma delta mi yi upon sigma delta mi. Z is equal to sigma delta mi zi upon sigma delta mi. As we make a bigger and bigger, and each delta mi smaller and smaller, the expression becomes exact. In this case, we denote the sum of I over integral. So we can write sigma delta mi is equal to or tends to, we can write integration of delta m dm, which is equal to m. Again, sigma delta mi xi can be written as integration of x dm. Similarly, sigma delta mi yi can be written as y dm, and sigma delta mi zi can be written as z dm. Here, m is the total mass of the body. The coordinates of the center of mass now are x is equal to 1 upon m x dm, y is equal to 1 upon m y dm, and z is equal to 1 upon m z dm. This is equation 7.5a. The vector expression equivalent to this scalar expression is r is equal to 1 by m integration of r dm. This is equation number 7.5b. If we choose the center of mass as the origin of our coordinate system, r x y z is equal to 0. That is, integration of r dm is equal to 0. That is, integration of x dm, integration of y dm, and integration of z dm is equal to 0. So these are normal concepts. Now let us find out the center of mass of a thin rod which is lying in the x-axis. So let us consider a thin rod whose width and breadth in case of cross section of rod is rectangular, or radius in case of cross section of the rod is cylindrical, is much smaller than length. Taking the origin to be at the geometric center of the rod, the x-axis to be along the length of the rod, we can say that on account of reflection symmetry, which we have done in the maths section in class 10th, for element dm of the rod at x, there is an element of same mass dm located at minus x. The net contribution of every such pair to the integral, and hence the integral of x dm itself, is 0. So equation 7.6, the point for which the integral itself is 0, is the center of mass. Thus the center of mass of the homogeneous thin rod coinciding its geometrical center. So this can be understood on the basis of reflection symmetry. So let me give some hint. What is reflection? So consider this as a mirror. So consider a small object dm is of mass dm is placed here at a distance x from the origin. So now consider this as a mirror. So a reflection of the same small particle the image will form here at minus x. So in this way, all the pair, so if there is a object, its image will form here. If there is an object, its image will form here. So total center of mass or total integral of the whole system is 0. And since and in 7.6, from equation 7.6, if that is the condition, that total integral of a center of total integral of a system is becomes 0, that means the center of mass is mass pass through the geometric center. Center of mass and geometric center are same, or center of mass coincides with the geometrical center. Now let us go through the example 7.1. The example says that find the center of mass of three particles at the vertices of equilateral triangle. The mass of the particles are 100 gram, 150 gram and 200 gram respectively. Find each side of the equilateral triangle is 0.5 meter long. So in this case, this is y-axis, this is x-axis. We have considered one of the coordinate, or one of the particle falls into the origin, that is 100 gram. Particle weighs 100 gram, falls into the origin, is in the origin. Particle weighs 200 gram, is here. Particle weighs 150 gram, is in the x-axis. Now since it is a equilateral triangle, therefore all the angles are 60 degree and all the sides are equal. Since all the sides are equal, so if if we draw a perpendicular here, then this side will also be equal to this side, means this will be the midpoint. The whole length of the side is 0.50, therefore the midpoint length is 0.25. So the coordinate of the midpoint is 0.25 comma 0. Now we know that this is 0.25, but we don't know the height. Height, how can we find? We'll write just tan 60 degree is equal to b, let this be d, bd upon bd upon od. So bd, so which implies that root 3 is equal to bd is uh, bd we don't know, and od is 0.25. So BD will be equal to 0.25 root 3. So here if you see this value 0.25 root 3, so we know the coordinate of B also. So all the three coordinates are known to us. Now just we will implement, and all the distance are also known. So just we will implement in the formula x is equal to m1 x1 m2 plus m2 x2 plus m3 x3. Just put the values and you can find out the answer. Similarly for y also, just put the values m1 y1 plus m2 y2 plus m3 y3 upon m1 plus m2 plus m3. So you got the value of y also, and that is the center of mass, or coordinate of the center of mass. Now let us do another sum. Find the center of mass of a triangular lamina. A lamina triangle LMN may be subdivided into narrow strips each parallel to the base MN, as shown in the figure 7.10. Now by symmetry, each strip has its center of mass at its midpoint. If we join the midpoints of all the strips, we get the median LP. So let me explain. So let us divide this into parallel strips which are parallel to Mn, and the center of mass of each strip falls here, falls here, falls here, falls here, and falls here. Now we can draw a line, the point joining them. The line is LP. The line is LP. Now, which is the median? Which is the median? So all the center of masses falls in LP. Similarly, all the center of masses lie on the other medians MQ and NR. This means the center of masses lies on a point concurrent of the three median, that is the centroid of the triangle, that concurrent on the medians of the medians, that is centroid G of the triangle. Let us see the next example. Find the center of mass of a uniform L-shaped lamina, a thin flat plate with dimension as shown. The mass of the lamina is 3 kg. So it is shown here. So let us see the answer. Choosing the x and y axis as shown in the figure 7.11, we have coordinates of the vertices of the L-shaped lamina as given in the figure. We can think of the L shape is consist of 3 squares, each of length 1 meter. The mass of each square is 1 kg. Since the lamina is uniform, the center of masses or center of mass C1, C2 and C3 of the squares are by symmetry. Their geometric centers and have coordinates half, half, 3 by 2, half, half, 3 by 2 respectively. We take the mass of the square to be concentrated at the points. The center of mass of the whole L shape XY is the center of mass of these mass points. So this is simple. So everything is given in the figure, just you have to find out. What it is telling. So there is a L-shaped structure. You have to find the center of mass for this. Values are given from the figure. So taking the values from this figure, and you can find out the center of mass of the system. So x coordinate will be, so you have to implement the formula, basic formula, m1 x1 plus m2 x2 plus dot 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 mn xn upon m1 plus m2 plus m3 dot 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 mn. So just put this formula here, find the value of x and find the value of y. The center of mass of L-shape lies on the OD line OD. We could have guessed this without calculation. Suppose the three squares make up the L-shaped lamina of figure 7.11. The different masses had different masses. How will you then determine the center of mass of the lamina? So now Today we'll leave till here only. Before closing the session, let us recap what we have done. So we have started with center of mass. So first we have done the definition of center of mass. So next we have find out the center of mass for a two particle system, and the center of mass value was m1 x1 plus m2 x2 upon m1 plus m2, and we have found the special condition where m1 and m2 are equal. What is the center of mass? So we found that it is the midway between the two particles. If there is n, thirdly we have found the if there is an n particle system, then what is the center of mass? So we have written uh, uh, that in the form of sigma. Again, we have found the center of mass. Mm, we have found the vector representation of the position vector uh, and the vector of center of mass, and again we have found the center of mass of a three particle system, and special cases we have done when the particles are equal. Now we have done, or we know came to know the conversation of or conversion of sigma into integration. So we also have learned the integration way to represent the center of mass. After that, we have tried to find the center of mass of a uniform thin uniform rod, and next we have done a few problem sums, example 7.1 and example 7.2. Also we have done example 7.3. So we have completed the center of mass topic of this lesson. Now till here it is done. We'll start in our next class. We'll start motion of a center of mass. Till then, goodbye and thank you for watching our videos, and please give a like son if this you like this video, so that it will encourage us to make more and more beneficial videos for you. And the people who have not subscribed it, please subscribe and click the bell icon so that you won't be missing any of the videos. Thank you very much.